Hello everyone, I'm Haoying Zhang, and I'm a PhD student from Insa-CVL and Inria. So this is a joint work with my supervisors and some collaborators from ENSTA Paris and the University of Carlos III. So this is a work about matrix profile. So what is that? It's a time series mining structure that stores some distance between any subsequences within the time series with its nearest neighbor. So when we consider a time series as an ordered vector of a certain length of n, we can split it into smaller subsequences of a certain length m, which is much smaller than n. And then we can compute some distances between each subsequences. And then we can store them into a matrix. It's called distance matrix. And then we can apply some functions like minimum and argmin at each columns of the matrix. And we store this data into two separated vectors that we call the matrix profile distance and matrix profile index. And these two vectors composed what we call matrix profile. Okay, so that was the formal definition of matrix profile. And now I will give you a running example. So here you have an ECG data. So it contains heartbeat patterns. And then with the matrix profile, it will transform it into another vector like this. And here I only show the matrix profile distance vector. So why is it useful? So with this example, if we have a look at this blue vector, which is the matrix profile, we can obviously see two peaks. And these two peaks are actually indicate two heartbeat anomalies in the original time series. So that is why it's useful. It's very easy to do some data mining, time series data mining tasks like anomaly detection in regular pattern time series or similarity discovery in irregular pattern time series, and also time series annotations. So it's very easy to use, so it becomes very popular in time series mining community. And recently, it attracted more attention because it has been proposed to as a privacy-enhancing technology. Why? Because it's a transformation of the original time series, and it contains argmin and min, so are nonlinear functions. And what is important is that it preserves good utility in downstream applications. So some examples of using MP as a pet, for example, to generate some synthetic time series by preserving the matrix profile, or to propose some privacy-aware matrix profile against the pattern inference, or using matrix profile as a privacy-enhancing features to be used in some machine learning pipelines for tasks like continuous authentication. And the gap is that despite all these various applications, there is no systematic privacy evaluations of this matrix profile. So without that, we want to answer the question that does publishing a matrix profile really satisfy the privacy criteria required by data protection regulations? So precisely our key contributions, including first, we formulate the risks of matrix profile sharing based on well-known privacy risks, including singling out to isolate an individual's record or linkability to try to link more than two records, or inference like given the matrix profile, is it possible to infer some sensitive attributes like age or sex? And secondly, we propose a reconstruction technique based on an optimization problem as our attack primitive. And finally, we evaluate it on three sensitive datasets. So in our privacy attacks, we consider a threat model where the attacker can have different types of auxiliary knowledge. We consider an attacker from having a weak knowledge by knowing only the generic type or the shape of the time series, to a strong attacker that can even know a full time series of an individual. So when we consider a strong attacker, it can actually do some naive attacks, but these attacks will become very limited when we decrease, like when we consider the weak auxiliary knowledge. So that's why we need a reconstruction to recover the original time series from its transformation matrix profile. And this reconstruction is an attack in itself that we refers to the original value inference that enters into the inference category, and also a building block that can enforce other privacy attacks like singling out linkability or attribute inference. So our reconstruction attack is based on an optimization problem that given a matrix profile MPT, and we consider attacker also know how to compute this matrix profile. So the objective is to find the T star, that is the argument of the loss function between the matrix profile of all the candidates T hat and the target MPT. So for the sake of performance, we also use a differentiable objective function. So the objective becomes to find the T hat that minimize this loss function that includes a squared arrow to the target MPT to encode the equality constraints and the ReLU function to penalize the violations of the inequality constraints. So you are welcome to see more details at the poster section. So the algorithm is that we initialize a set of fuzzy time series T hat, and then we refine it with a solver to minimize the discrepancy between their MP and the target MPT. So this optimization problem is based on an assumption that we should retrieve the original time series by approximating the matrix profile. However, the matrix profile function is not injective, which means that several inputs can map to nearly the same matrix profile. For example, two symmetric time series will have the same matrix profile. In consequence, the optimization will not be determinist, that can converge to different local minima, which do not always match the real input. So to address this problem, we first did a parameter study, and we found that by simply decreasing the subsequences length m, it can already largely mitigate the problem and improve the convergence. And in the rest of the case, we propose also a domain-specific post-processing that requires only some ad hoc knowledge. So for example, here, if we have a ECG data, so here at the left, you have the yellow lines, which is the reconstruction after the optimization problem, and the red lines are the ground truths. And so since the attacker knows that it's an ECG data, he can recognize some zones in the heartbeats, and then he can use also some ad hoc ratios to rescale the different zones. So in order to improve the reconstruction quality. So for the evaluation, we evaluated the different privacy attacks as well as the reconstruction technique on 3 data sets, including ECG as the physiological data and energy consumption data set and smartphone accelerometer data set. As for the metrics, we use Pearson correlation coefficient and root mean square error for evaluating the reconstruction quality. And for singling out and linkability attacks, we use success rate and then accuracy and F-score for the attribute inference attack. So the result in the nutshell, here I give some examples. So here you can see the yellow lines and the red lines are very highly overlapped, which means a very successful reconstruction. Statistically, we have a Pearson correlation up to 0.99 and RMSE as low as 0.03, meaning very fiddle reconstruction. And when we use this reconstruction to evaluate the privacy attacks, we have up to 100% for singling out, 95% for linkability, and 90% of the accuracy and the F-score for sensitive attribute inference. So these results break the prior claims in the literature that matrix profile is not invertible, hence privacy preserving. So the message that I want to convey is that matrix profile is not private. So it's actually invertible and vulnerable to all these attacks. So it should not be adopted as a pet on its own. As for future work, we can imagine to scaling the attack with longer subsequence length. We can study some additional privacy attacks like re-identification attack. And finally, to design some countermeasures to eventually propose a pet with matrix profile by adding, for example, some DP noise and also evaluate the utility loss. So that's it. Thank you, and see you at the poster station.